Hello students, welcome to Ma'am and Me Academy. I am your mathematics educator Bipul Babu. Today let us continue our chapter Real Numbers. In the previous video we discussed about type first question, which was to find the HCF of two numbers using Euclid's division algorithm. Now today we will discuss the second type of question, which is a word problem based upon this Euclid's division algorithm. Now let us see the example 2. In the previous video we discussed about example 1 and I gave you a homework to do. I hope you have done that. Okay. Now example 2 says, show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. See, this is very simple type of question. Let me tell you the trick. As you know that in Euclid's division lemma we write a is equals to bq plus r. So we will use this concept to prove this. Now in Euclid's division lemma there were two unique integers, to begin with, a and b. So we will assume a and b here also. Let us see. While you read this question, you will understand that you have to take a as the positive integer, because we are talking about positive even integer as well as positive odd integer. You need both type of integers, right? So we will assume that let a be any positive integer. What is a? It is any positive integer. Now what will be the value of b? And let b is equals to, for this I have a trick for you. Consider the coefficient of q in any question. Okay, consider the coefficient of q, that will be the value of your b. Okay, so in this question it will be your 2. Now according to Euclid's division lemma, how do you write that? A is equals to bq plus r, right? A is equals to bq plus r, or you can write, substituting the value of b here, you can write a equals to 2q plus r. And what was the condition? 0 is less than equals to r is less than 2, right? Here it was b in the statement, now we'll use 2 here. Okay, so what I have done that I have written the Euclid's division lemma. Now I substituted the value of b here. Okay, and the condition in the statement was like this, right? So I have substituted the value here as well. Okay, now the remainder, what can be the value of remainder? Yes, the remainder can be 0 and 1. I have told you that the remainder can never be equal to the divisor. Okay, so there will be two cases. Case first, when r equals to 0. This is your case first, when the remainder is 0. Now what happens when r is 0? What will be the value of a? Put r equal to 0 here. You will get a is equals to 2q, right? R is 0, so you will get a equals to 2q. Can you tell me whether it is divisible by 2 or not? Yes, it is divisible by 2. If you can see in the rough that 2q divided by 2, you will get q. That means this particular number is divisible by 2, which means that it is a what? Even number, even integer, right? So you will write it in the bracket, even. Now let us see the case second. Case second is when r equals to 1. Okay, when r equals to 1, put it here. You will get a is equals to 2q plus 1. Is this particular number divisible by 2? Can you tell me? No. Why? Because 2 is not coming in common from this whole expression. right? If you can see in the rough, you can see this 2q plus 1 when divided by 2 will not give you any quotient. Why? Because this 1 is extra. If had it been 2, then it would have been what? Even integer. So this is what? Odd integer. Now what happens is that after doing this, you came to know that any even integer will be of the form 2q and odd integer will be of the form 2q plus 1. Now how will you conclude this question? You will conclude this question by writing the question itself. Funny, isn't it? See, you will write in the end that from here, every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Let me just revise it for you. Okay, let us see what we have done. We took two numbers. Let a be any positive integer and let b equals to 2. From where this 2 came? It came from the coefficient of q. Okay, I think you might not be able to understand it with the one question. We'll discuss the another question, then you will come to know. Now, let a be any positive integer and let b equals to 2. Then we wrote according to the Euclid's division lemma. According to Euclid's division lemma, a equals to bq plus r. Okay, here we substituted the value of b, which is 2. A equals to 2q plus r. And the condition in the Euclid's division lemma was 0 is less than equals to r less than b. So we substituted the value of b here. 0 is less than equals to r less than 2. Now I asked you how many values can r hold. Now what can be the values of r? It can be 0 and it can be 1. Okay. So case first, when the remainder is 0, so we put the value of r here as 0. You will get a equals to 2q, which is even. I told you how. Okay. And in the second case, when remainder equals to 1, a equals to 2q plus 1. This is odd. So we'll conclude the question by writing in the end, because there is no space left here. So you will write in your copy as every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Now let us see your example 3, which is a similar type of question only. Let me just rub it for you. Question example 3 says, show that any positive odd integer, you can see from your book also, show that any positive odd integer of the form 4q plus 1 or 4q plus 3, where q is some integer. This is your example 3 in your book, and this is similar type of question which we have done in example 2. Now what it says that show that any positive odd integer is of the form 4q plus 1 and 4q plus 3. Now here in the question only one type of integer is asked. What is that? Odd integer. In the previous question it was asked odd as well as even. So we assumed a to be an integer. Okay, now we'll assume let a be any positive odd integer. We want only odd integer here. So we are assuming a to be positive odd integer. If in the question it was said that positive, odd as well as even, then we'll assume that a as positive or positive integer. Since it is asked only for the odd integer, we'll assume a to be a positive odd integer. Okay, now, and what will be the value of b? I told you the trick that coefficient of q will be the value of b. So here the b will be 4. Now let us write the Euclid division lemma according to Euclid division lemma. A equals to bq plus r. Okay, and we'll substitute the value. A equals to b is 4q plus r, and what was the condition? Condition was that 0 is less than equals to r is less than 4, right? Okay, now tell me what can be the value of r. It can be 0, 1, 2, 3. Okay, can it be 4? No. Okay, because the remainder can never be equal to the divisor. So in all we'll get 4 cases, right? For 0, for 1, for 2 and for 3. Let us see all of the cases. Case first, when remainder is equals to 0. When the remainder is 0, what will happen? We'll substitute 0 here. You'll get a equals to 4q. Okay, now can you tell me, is it odd or even? Yes, it is even because it is divisible by 2. So it is even, and what we need is here, it is odd. So we don't need here, we don't need this, right? So we'll not consider this. We'll see the case second. Write it here. When r equals to 1. Okay, case second is when r equals to 1. Substitute here. You'll get a equals to 4q plus 1. Is it even or odd? It is odd, right? So we'll write it in bracket that it is odd. Now case third. When r equals to 2, right? When r equals to 0, r equals to 1 and r equals to 2. What you'll get? A equals to 4q plus 2. Now can you tell me, is it even or odd? Acha, tell me that, are you able to identify whether it is even or odd? Let me tell you that, try to take 2 as common. Okay, in this expression you can take 2 as common. See how? 2q plus 1. Okay, this way. And since you are able to take 2 as common, so that means this is even number. Here you can't take 2 as common, so it is what? Odd. Let us see the case fourth, which is when r equals to 3. R equals to 3. What you'll get? You'll get a equals to 4q plus 3. Are you able to take 2 as common here? No. That means it is odd. So you saw all 4 cases. What you got? You got that in the case second it was odd, in the case fourth it was odd. And what was the form? 4q plus 1 and 4q plus 3 as given in the question. 4q plus 1 and 4q plus 3. So this was the solution. Now how to conclude? I told you from the question itself you can conclude that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Okay, till here you have to write. After finishing this, you have to conclude the statement question that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. I hope you understood this. Let us see the exercise. I'm not proceeding to the next example, which is example 4, because it's a word problem of another type. Okay, let us finish this particular type of question from the exercise as well. Then we'll see the word problems based on Euclid's division algorithm. Let us see the second question from exercise 1.1, which says, show that any odd positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Now let us write, let a be any positive odd integer. Why are we writing odd here? Because it is said in the question that we only want the odd integers. So let a be any positive odd integer and let b equals to, now what will be the value of b? What was the trick? Yes, the coefficient of q will work as the value of b. Now according to Euclid's division theorem, lemma, according to Euclid's division lemma, which says a equals to bq plus r, right? A equals to bq plus r, and now we will substitute the value of b here. So we will get a equals to 6q plus r, and what was the condition? That 0 is less than equals to r less than b, right? So the value of b is 6. Now what will be the value of r? The value of r can be 0, 1, 2, 3, 4, 5 and 6, right? That, sorry, not 6, okay, because the remainder can never be equal to the divisor. In the flow I said that, but it is not there. Now what we'll do, we'll make the cases. How many cases will be there? There will be 6 cases, right? Starting from 0 to 5. Now let us see each case. The case first is when remainder is 0. When the remainder is 0, then you will get what? A equals to 6q. Now tell me whether it is odd or even? Yes, it is even. Why? Because it is divisible by 2. So we don't need to pay attention to this because we only need the positive odd integer. Okay, now let us see the case second, which says when r equals to 1. When r equals to 1, your number will become a equals to 6q plus 1, right? A equals to 6q plus 1. Now, is it odd or even? Yes, it is odd. So we'll write it in the brackets. Now let us see the third case, which is when r equals to 0. When r equals to, r equals to 2. Okay, now when r will be 2, your number will become 6q plus 2, right? 6q plus 2. As you can see that you can take 2 as common here, right? So that means this is even and it is of no use to us because we are only considering positive odd integer. Now let us see the fourth case, case 4, which says when r equals to 3, right? When r equals to 3, the number will be a equals to 6q plus 3. Now can you take 2 common here? No. That means this is odd. Okay. Now let us see the case 4th, then case 5th. Okay. Case 5th is when r equals to 4. This is very simple type of question and very scoring. Okay. When r equals to 4, a will be 6q plus 4. All of you can see that 2 is common here. That means this is even and it is of no use to us for this question. Okay. Now let us see the case 6th, which says when r equals to 5. Okay. Now a equals to 6q plus 5, right? We'll substitute the value of r here. You'll get 6q plus 5. That means this is odd, right? Now all the cases are over. Is there any case 7 when r equals to 6? No, because the remainder is never equal to the divisor. Now you saw all the cases. What did you conclude? That you concluded that all the odd integers, you can see all the odd integers are of the form, either of the form 6q plus 1 or 6q plus 3 or 6q plus 5, which was asked in the question, right? Now how will you conclude? I told you that you have to conclude from the question only, which says that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. I hope you understood this. Very simple. You have to assume the value of b. The value of b is a main part here. If you are able to guess the value of b, you can do the cases very simply. Now let us see the fourth question, because the third question is of different type. We'll discuss in the next video. The fourth question says, let me just rub it for you. Fourth question says, use Euclid's division lemma to show that the square of any positive number integer is either of the form 3m or 3m plus 1. Okay, 3m or 3m plus 1 for some integer m. Now it is a little bit different question. It is a little bit different question, but the similar one only. Fourth question. Okay, now let a be any positive, what should I write? Positive integer or positive even integer or positive odd integer. See the question once again. It is said to show that the square of any positive integer. That means we have to assume a as any positive integer, right? Now, and b equals to, what will be the value of b? This will be the coefficient of m. Okay, the coefficient of m is 3. Now let us proceed. Let, according to Euclid's division lemma, which says a equals to bq plus r, right? And when we will substitute the value of b here, you will get a equals to 3q plus r, and what is the condition? 0 is less than equals to r is less than 3. Now what is said in the question? That you have to square the positive integer. Till now what we were asked that it is of the form this and this. Okay, we didn't have to do any squares or cube. Now in this particular question it is said that you have to take the square of positive integer. Now case first, when r equals to 0. When r equals to 0, you will get a equals to 3q. But this is not enough. It is said in the question that you have to square this 3m or 3m plus 1 is the form of any square. Okay, it is representing the square number. So we will square this number. Let us square. On squaring both sides, on squaring both sides, you will get a square is equals to 9q square, right? 3 will be squared and q will be squared. You will get 9q square. Now you would be asking that it is not of the form 3m or 3m plus 1, but we can make it. How? Let us see. We can write 9q square as 3 into 3q square, right? Can we write it? 9q square equals to 3 into 3q square. Now let us assume this bracket as m, right? So let us write a square equals to 3m, and we'll mention that where m equals to 3q square. Now see, is it of the form 3m? Yes. We have made the question according to our need. Now let us see the case second. I am using a different pen so that you might not confuse. Case second, which says when r equals to 1. When r equals to 1, what you will get? You will get a equals to 3q plus 1. You will get 3q plus 1. Now what we have to do? We have to square it. On squaring, we will get a square equals to 3q plus 1 whole square. Right? Let us open the bracket. You will get 9q square plus 1. Is it enough? No, because this is the identity a plus b whole squared, right? Which says a square plus b square plus 2ab. Okay, so a square is 9q square. This is 9, okay? And b square, that is 1 square, is 1 plus 2ab. That means 2 into 3q into 1. You will get 9q square plus 3 to the 6, 6q plus 1. Right? Now, can you make this either of the form 3m or 3m plus 1? You are getting a hint. You can see that 1 is left here and 1 is here also. That means we can convert this particular expression as 3m plus 1. Let us see how. Can you take 3 common from all 3 terms? No, but you can take 3 common from the 2 terms, right? We will take 3 common, which will be 3q square plus 2q plus 1. Okay? Now, let us assume the bracket as m. A square is equals to 3m plus 1, where you have to mention what is the value of m. You have assumed that where m equals to, what is this? 3q square plus 2q. Okay, now is it of the form 3m plus 1? Yes, we have modified the question. Now let us see the case third. Since there was not much space left, so I have cleared it for you. Now the case 3 is when r equals to 2, right? Your number will be a equals to 3q plus 2. Now what we have to do? We have to square it, right? On squaring it, we will get a square equals to 3q plus 2 whole squared, which will be a square equals to 3q square is 9q squared plus 2 squared is 4 and 2ab is 2 into 3q into 2, which will be ultimately equals to 9q square plus 4 plus 12q. Now, is it of the form 3m or 3m plus 1? You will be confused, right? Because there is no 1 here, so you can't say that it is of the form 3m plus 1, and you cannot take 3 common from all 3 terms, right? So you cannot say that it is of the form 3m. Now what we will do? We are in the dilemma, right? We'll try to, I have told you that we will modify the question as per our need. You can see that you can take 3 common from here and here, right? But you cannot take 3 common from 4. But we can break 4 to get 3. Let us see how. We can write here as, let us first write together the both numbers from which we can get 3 as common. So 9q square plus 12q plus 4. Now I can write 9q square plus 12q. I can write 4 as 3 plus 1. Can I write? Yes. Now you can take 3 common from all these 3 terms and 1 will be left as a remainder, right? So you will take 3 as common here. You will get 3q square plus 4q plus 1 bracket close and plus 1. You will assume the bracket as m, right? So you will get a square equals to 3m plus 1, where m is equals to, what is in the bracket? 3q square plus 4q plus 1. Okay, now how to conclude? See, this is of the form 3m plus 1 only, right? If you're not getting exactly the same which is asked in the question, try to modify it. Okay, try to break some number. Okay, so let us conclude this question. What is in the question? It says use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So we will conclude this question as that the square of any positive integer, don't need to write that use Euclid's division lemma. You will write from here that square of any positive integer is either of the form 3m or 3m plus 1 for some integer. That is all for today. I'll see you in the next video with the last question of exercise 1.1, and I'll also continue the word problems based upon Euclid's division algorithm. Till then, be happy, be safe, and stay at home and study with Ma'am and Me Academy. We are there for you to help you. Thank you.